Welcome to today's lesson on composition of functions. Imagine a scenario where you first enter your PIN into an ATM and then withdraw cash. Each step processes your input to produce a final result. Similarly, in mathematics, composition of functions involves applying one function to the result of another. Let's talk about the composition of functions. This is the process of merging two functions to create a new one, where the output of the first function becomes the input for the second. Simply put, one function's output feeds directly into another function. Now let's write that mathematically. Suppose we have two functions, f and g. The composition is written as f composed with g of x. What does it mean? It means we first apply g to x, then we plug that result into f, so we get f of g of x. So remember, start with the function closest to x, then work your way out. That's the power of function composition. It builds a pipeline between functions. Let's take a real-life example to understand composition of functions. Imagine you have two functions. Function f converts temperature from Celsius to Fahrenheit. Function g converts Fahrenheit to Kelvin. Now, if you want to convert a temperature directly from Celsius to Kelvin, you can compose these two functions. That means, you first apply f to convert Celsius to Fahrenheit, then apply g to convert that Fahrenheit value to Kelvin. You start with a temperature in Celsius, pass it through f, then through g, and just like that, you've converted it straight to Kelvin. This is the power of function composition, chaining operations together to make complex processes simple. Here's something important to remember: not all functions can be composed freely. Sometimes, domain restrictions make a composition undefined. Let's look at an example. Suppose we have two functions. Function f to x equals natural logarithm function ln to x, g to x equals minus x. Now let's try composing them. F of g of x equals ln to minus x. Here's the problem. The logarithmic function ln to x is only defined for positive values of x. But g to x equals minus x flips positive inputs into negative outputs. So, if you plug in a positive number, you're taking the log of a negative number, and that's undefined. So in this case, f of g of x doesn't work for any positive x. To avoid mistakes like this, follow this three-step rule of thumb. When finding the domain of a composite function, step 1, find the domain of the inner function g to x. Step 2, find the domain of the composite expression f of g of x. Step 3, take the intersection of the two domains. So before composing functions, always check if the output of the first function is valid as input for the next. That's the key to safe and correct composition. Let's wrap up with the key properties of function composition, the rules that govern how functions combine. First is associativity property. For functions f, g and h, composition is associative, which means f composed with g, then composed with h, is equal to f composed with g composed with h. You can group them however you like, the result stays the same. Second is commutative property. This one's tricky. Composition is commutative only if f composed with g equal to g composed with f, and that's not always true. So always check before assuming commutativity. Third is identity property. The identity function, written as I of x equal to x, acts like a neutral element in composition. For any function f, f composed with I equal to I composed f equal to f. Fourth is inverse property. If a function f has an inverse, then composing them cancels out the effect. F composed f inverse equal to I equals f inverse composed f. These properties help us understand how functions interact. Whether we are simplifying, reversing, or combining operations. Let's summarize what we have learned. Composition of functions means applying one function to the result of another. F composed with the composition of g and x equals to f of g of x. The inner function g of x is evaluated first, then its output is passed into the outer function. F composition is not commutative, i.e., f composed g is not equals to g composed f, but it is associative. To find the domain of f composed g, take the intersection of domain of g of x, domain of f of g of x. The range of the composition depends mainly on the outer function applied to valid inputs from the inner function.